Like in the classroom, prepare yourself for the lesson ahead. Silently prepare your materials for math. It will be best to have writing materials with you. You may use a notebook or a printout of the Learning Worksheet 2.1. Kindly settle down. Continuity at a number and on an interval. What does the word continuous mean? An unbroken whole, non-stop, without pause, uninterrupted. How can these ideas be translated into graphs of functions? As you trace this graph, there is no part when you have to stop or lift your pen. Same thing for this graph. As well as for this trigonometric function. In tracing this curve, you will notice a break when x is negative 2 and when x is 2. In this next function, you have to lift your pen at x equals 0. While in this graph, there is a pause when x is negative 2 when you reach the whole. What conditions made these functions not continuous? F of negative 2 is not defined. Limits as x approaches negative 2 and 2 do not exist. F of 0 is not equal to the limit as x approaches 0. Considering the examples shown, when is a function continuous at the x value c? A function f is continuous at c when f of c exists. When the limit of f of x as x approaches c exists, and the limit of f of x as x approaches c is equal to f of c. Let us use these conditions in checking if a function is continuous at a given x value. Is a of x equals the quantity x minus 9 over the quantity square root of x minus 3 continuous at 9? We check each condition starting with finding a of 9. Since the function value is indeterminate, we will rewrite the function in order to cancel the common factor. After canceling the quantity x minus 9, we apply substitution to the new expression square root of x plus 3. And therefore, the limit of a of x as x approaches 9 is 6. And since the last condition is also not satisfied, we conclude that A is discontinuous at 9. For the next example, determine if b of x equals the square root of quantity 2x plus 5 is continuous at negative 1. B of x is defined when 2x plus 5 is greater than 0 or x greater than negative 5 halves. For the first condition, since negative 1 is greater than negative 5 halves, then b of negative 1 exists. In finding the limit, we substitute negative 1 to x, obtaining square root of 3. Since b of negative 1 is also equal to 3, then the limit of b of x as x approaches negative 1 is equal to b of negative 1. Therefore, b is continuous at negative 1. Moving on, we check if c of x equals 2 over the quantity x minus 2 is continuous at 2. By substitution, we obtain c of 2 equals 2 over 0, therefore, c of 2 does not exist. And so, c is discontinuous at 2. Looking at its graph, we find a vertical asymptote x equals 2 since the limit of c of x as x approaches 2 from the left is negative infinity, while the limit of c of x as x approaches 2 from the right is positive infinity. In the next example, given the graph of d is d continuous at 1, we find in the graph that d of 1 is equal to 2. While the limit of d of x as x approaches 1 does not exist, since from the left of 1 the limit is 1, and from the right of 1 the limit is negative 1. Hence, d is discontinuous at 1. In this first example, the function is discontinuous at 9. Looking at its graph, we find a hole at x equals 9. This is an example of a removable discontinuity where the limit of f of x as x approaches c exists, and either f of c does not exist or f of c is not equal to the limit of f of x as x approaches c. The discontinuity may be removed by redefining f of c so that it will be equal to the limit of f of x as x approaches c. We also encountered this function c, which was discontinuous at 2. We recognized the infinite limits as x approaches 2. This is an example of an essential discontinuity. If the limit of f of x as x approaches c does not exist, because the limit as x approaches c from the left or from the right is either positive or negative infinity, then f has an infinite essential discontinuity at x equals c. Now, given the graph of d, it is discontinuous at 1 since the limit of d of x as x approaches 1 does not exist. This is an example of a jump discontinuity. If the limit of f of x as x approaches c does not exist because the limits from the left and right of x equals c both exist but are not equal, then f has a jump essential discontinuity at x equals c. These were the other examples we encountered earlier wherein the functions were not continuous at particular x values. Can you name the type of discontinuity of each graph? This is an essential discontinuity. This has a jump discontinuity. And this is a removable discontinuity. Defining the function at negative 2 to be equal to 3 makes the function continuous at negative 2. Let us now apply the conditions for continuity at a number in solving this problem. For what values of p and q make the function k defined as follows, continuous at every number? Recall the conditions for continuity at a number. Each of the three parts of this function are continuous at all x values within the specified intervals. K of x is also defined at any real number including 1 and 4. We just need to make sure that the limits from the left and from the right of 1 and of 4 are equal for the limits to exist. To satisfy this, we equate x and px plus q if x is 1 and px plus q equals negative 2x if x equals 4. We then substitute the indicated x values resulting to this system of equations. 1 equals p plus q and 4p plus q equals negative 2 times 4. With these equations, what are the values of p and q? Solving the system of equations, we obtain p equals negative 3 and q equals 4. Lastly, recall the interval notations. The following are the different possible scenarios for continuity on an interval. Determine all intervals for which f of x equals the quantity x plus 2 all over x times the square root of quantity x plus 2 is continuous. From our knowledge of domain of rational and radical expressions, f is undefined when x is 0 or negative 2. F is defined only when x is at least negative 2. Since there are no function values when x is smaller than negative 2, the first interval where f is continuous is when x is less than negative 2 but greater than 0. Note that it is an open interval since f of x is undefined at negative 2 and 0. Since there are no other restrictions beyond 0, then f is continuous in the open interval 0, positive infinity. We verify these intervals through this graph. Please refer to Learning Worksheet 2.1 and the textbook for additional examples. Similar problems and other applications are found in the textbook as well.